No.
Um, Hi, good day. So this is the phase field methods and mathematical modeling group. And with me here is Matthew and Osaro. So I will just move to the next slide to introduce to us what phase field methods and mathematical modeling is. So you can see a picture of an ice cream changing phases from a solid phase down to kind of an aqueous phase or a liquefied phase, right? So the phase field model is a mathematical and computational approach that can be used to describe or help us to understand how this phase transition works in any system, mostly for solid systems. And they so generally they simulate the evolution of interfaces and physical boundaries. And they kind of consider or track these phases using diffusion interfaces and free energy functional. When I say diffusion interfaces, what it does is that instead of pinpointing the exact boundaries between different phases of a material or a system, in this case, an ice cream, the PFM model uses variables that change gradually to describe these transitions. And for the free energy functional, what it does is that it uses a concept to predict how these phase changes occur by calculating the lowest energy state of the system, considering factors like boundary energies and external influences based on the principle of thermodynamics. Next slide. So here we just wanted to show a historical background on the PFM model. So in the early 1950s to the late 1970s, John W. Kahn and John E. Hilliard developed the equation for phase separation in binary alloys, then transitioned down to the present time now, where the model was modified by integrating computational methods to enable the model to simulate more complex systems. Next slide. So here we were trying to compare or show rather how PFM models are more advantageous in over other numerical models. So we compared the PFM model versus the lattice-Boltzmann method. So the lattice-Boltzmann method generally is a fluid dynamic model that simulates fluid flows using discrete particles on a lattice grid. So the PFM model directly models fluids as they naturally behave, making it easier to visualize complex fluid interactions. On the other hand, the lattice-Boltzmann method uses imaginary grids or particles to mimic how fluids behave under various conditions. And we also pointed out here that PFM can manage scenarios where we have three-phase fluids or three types of fluid interactions, which is more complex than the LBN method. And in the second point, we compared the PFM model versus the finite element method and the extended finite element method. And generally, the finite element method divides large systems into smaller, simpler parts called finite elements. And mathematical equations are then used to describe these elements, and they are solved to understand how the behavior of the entire system. While the extended version of the finite element method just um, integrates or shows the discontinuities within a system. But the PFM method is more advantageous in the sense that it can handle intricate patterns and boundaries in materials smoothly, making it great for studying how materials can change under different conditions. In contrast, both the XFM and the FEM methods need precise setups and adjustments to track where materials meet or separate. The downside or the disadvantage of the phase field model is that it requires a lot in its setup, which means more data and computing power to get accurate results. Next slide. So I'm going to call on the other student or Saro to take it off from here. Thank you.
Okay, thank you, Justice. Okay, here we'll be talking about the general principles of phase feed methods. First, we present a simple system of two phases, phase A and phase B. Between phase A and phase B, we have an interface. So we also introduce one of the fundamentals of the phase feed method, which is the order parameter. The other parameter is used to describe the evolution of this system with time. For phase A, the other parameter is equal to 0, and here it represents 100% of phase A. And when the other parameter is equal to 1, it represents 100% of phase B. So between 0 and 1, the other parameter represents like a mixture of phase A and phase B, which is basically like the interface. So next slide. Okay, then we'll talk about like the total free energy. The total free energy is like the summation of the chemical energy for both phase A and phase B, then the double well potential energy and the gradient energy density. The chemical energy basically represents the system when it is homogeneous for phase A and phase B. Then the gradient energy tries to like model the heterogeneity in the system. So it is like a gradient of the square of the other other parameter. Then we also have the interfacial gradient coefficient, which is A. Then the height of the double well potential energy. So the total free energy basically takes the shape of a double well function, which at the minimal point represents phase A and phase B. Here we have 0 for phase A and 1 for phase B. And in between, we have the height of the double well potential energy. Next slide. Okay, now we'll talk about the governing equations. The Alenkern equation is one of the fundamental equations which is used in phase feed modeling. Basically, it's like try to model the change of the other parameter with time. So it defines the change of other parameter with time. It relates it with the change of the total free energy with the other parameter, and then introduces a constant, which is the mobility of the phase feed variable. The mobility of the phase feed variable is defined by this equation below, and it's like the root of the formula is the root of 2 times the height of the double well function and m. M is like the mobility of the physical variable. So the total free energy as a function of the other parameter is defined as the change in the free energy as a function of the other parameter and the gradient of the free energy as it changes with the other parameter. Next slide. Okay, now we'll do like a simple hand calculation demonstrating how the Alenkern equation is used to model phase feed. It's used to model a phase feed. So we also present a simple system of two phases. Here we have a system of two phases with an interface. The delta here represents the interfacial length. Then Alenkern equation, which represents like the driving force, and the gradient, which is like just the diffusion of the system from one phase to another. Next slide. Okay, next step for us is to like discretize our order parameter. We use the first order Euler method in time integration, time discretization, and the second order central finite difference for spatial discretization. Then we calculated our initial order parameter using this formula here. Arrow naught is our initial position for our modeling. Next slide. Okay.
Okay,
I'll
thank
call
you,
on
Osara.
my colleague, just Matt, to continue from here.
Yes, thank you. Um, so now we're going to solve the Allen-Cahn equation in 1D. Here we've had it discretized in the last slide, and we also have the initial phase field profile. And so now we can define our variables here and establish the discretized time increment with the time step. And so we can solve the 1D equation starting by calculating our phase field variables. A is the gradient energy coefficient, which is the root of 3 times the interfacial energy sigma times B, which is a constant based on the thickness of the interfacial region. And then this is divided by delta, which is our interfacial thickness. And then next we calculate the double L potential energy, the height, um, which is equal to 6 times our sigma times delta over our B. And then lastly, we calculate the mobility of the phase field variable, which governs the evolution of the diffusive interface. And this is equal to the root of 2 times W over 6A, where M is our constant based on the physical mobility of the interface. And then we proceed to calculate the initial phase field between our phase A and our phase B. In phase B, we have the initial I is equal to 0, and then this is at x equals 0 on the domain. Tan H is a hyperbolic function, which includes W and A, and then x minus RO is our position on our along our x direction interface. The phase field in B is equal to 1, and then our phase field in A is equal to 0. Sorry. And so the results from this, using our discretized Allen-Cahn equation, we have the driving force term GA minus GB, and then our gradient diffusion term given by the finite difference method here. And so for each variable in I, we want to use delta X as the grid spacing increment and delta T as our time step. So for I, 1 to 20, which is our grid spacing index or our grid number, and then we use that with to calculate our phase field P at I, and our time our total time range is 1 to 400 seconds. And these figures below represent the phase field variable along with the sum of the driving and gradient energies at 1 second to 200 seconds. And so initially we have our phase field where in phase B it's at 1, and then it diffuses into phase A, which is at 0. And there's no driving or gradient terms here in the beginning, but as we continue with time, our phase field migrates towards phase A, and so we see this migration front um, uh, going along the x direction, and then we see an increase in our driving and gradient terms as well. And at 200 seconds, we see this phase going further into phase A. We see this diffusion, and then we also see a change in our driving and gradient energies. And then we created a numerical model in using COMSOL multiphysics software. It's a finite element software. And the model is based off of a paper from Zhao et al. 2018, which explores a phase field fracture model of a solid medium under tension.
And so this also includes a line crack as the fracture interface or a notch for that matter. And so we use built-in physics interfaces in COMSOL. One is solid mechanics to solve the linear elasticity terms. And then we also use the phase field damage interface, which couples the phase field with deformation or displacement of the crack and the medium. The weak form of two equations here is what COMSOL uses in its discretized solver. And so here we have the first equation, we have the Cauchy stress tensor, and then B delta U and F delta U are the external work done as body forces on the mesh and along the boundary. The second equation is the phase field evolution equation, which includes the fracture energy, and GC, which is the critical fracture energy density, as well as this LO term, which is the prescribed width of the phase field of the crack region. So it's the width of this crack region. The boundary conditions, so on the top and left boundaries, the displacement in the x direction is 0. These are roller constraints on the side, so it is able to move in the y direction. The bottom boundary is completely fixed, so there's no displacement in the x or y directions. And then the way we give the model tension with UT is a displacement load only in the y direction, and that moves with time. The initial conditions here, so we have the phase field is equal to 1 in the notch and 0 elsewhere along the domain. The physical properties that we use for this model are given in Zhao's paper as well. And the model is 1 millimeter by 1 millimeter, and the crack length is 0.5 millimeter. So these are the numerical results. The first two figures show the phase field, and we also ran two different cases. One case where our cracked width, or LO, is 7.5 to the negative 3 millimeters, as well as a larger width of 1.5 to the negative 2 millimeters. And so as we can see in this figure, where it is black, we have our phase field is equal to 0. And then once we get closer to the center of the crack, we have it increasing to 1. And so we see this in both figures. The difference that we want to point out is the thickness here. So the thickness here goes about 0.25 on each side, so about 0.5 millimeters. Whereas here we have slightly higher, and maybe goes up to 0.3, so this is 0.6, 0.75 millimeters. These bottom figures show the displacement in the y direction for the smaller cracked width, 7.5 to the negative 3 millimeters. This is at time equals 0, where we have a vertical displacement that is much smaller compared to what the displacement in the y direction is at 60 seconds. And so you can note that by this is to the power of to the negative 5, where it started at 10 to the negative 11 to at time equals 0. And we included a few example applications for the phase field method, which one can be applied to rechargeable batteries, which focuses on crack propagation during intercalation of lithium ions. And intercalation is basically the intrusion of a molecule, or cations in this case, into the surface or medium. This method is also used in fracture mechanics, so here in fatigue fractures, which is similar to our line crack problem. It can be expanded to incorporate thermal loads, chemical loads, and mechanical loads based on different pressures and temperatures. And then we can either solve these problems at a macro scale or down to the micro scale, or have a combo of the two. Another few examples is the um, coalescence of vapor or gas bubbles, and this incorporates the Navier-Stokes equations with the Korteweg equations, where we have a smaller gas bubble that diffuses into the larger gas bubble. And so the magnitudes of the velocities and the streamlines are given in these different colors here, with blue is equal to lower velocities, red are higher velocities. And the one last example that we have here is given in crystal growth. So this can be applied to rocks with recrystallization when they are exposed to various pressures and temperatures. And so we can see different different phases or different scales of crack growth with time increasing as they start small and they slowly diffuse along the grain boundaries, and then they get larger with time. And that is our presentation. Thank you for taking the time to review it. Thank you.
Thank you.